This video is on testing a hypothesis about a population proportion. Basically, it's the same song, second verse. Testing a hypothesis concerning a population proportion is nearly identical to testing a hypothesis about a population mean. The major changes in the procedure include the use of the population proportion p in the formulation of the hypothesis rather than the population mean mu, and similar changes in the calculation of the test statistic. The lesson goals are to, first of all, determine the null and alternative hypotheses, then calculate the test statistic and calculate the p-value, and then make a decision to reject or fail to reject the null hypothesis, h sub 0, and finally state the conclusion about the original hypothesis or claim. Some examples of hypotheses about p are, first of all, in the upper left-hand corner, an original claim or hypothesis that 60% of students are in favor of a new registration system. So that's a claim about a percentage or proportion, p, 60%. The null hypothesis is that the proportion is 60%, which is the claim in this case. And the alternative hypothesis is that the proportion is not 60%. Now, in the upper right-hand corner, if the original claim or hypothesis is that the proportion of students who are in favor of a new registration is not 60%, then the claim is the alternative hypothesis, because the null hypothesis always has to be that the proportion is equal to some value, in this case, 0.6 or 60%. In the lower left-hand corner, we see an example of a claim or hypothesis that says that more than 60% of students are in favor of a new registration system. So that claim is also the alternative hypothesis because it is stating that the proportion differs from 60%, in this case that it's more. Again, the null hypothesis always has to be that the proportion is equal to some value because the null hypothesis is the underlying assumption of the test. And so it has to have a specific value for the population proportion to use in calculations. And finally, in the lower right-hand corner, the original claim or hypothesis is that less than 60% of students are in favor of a new registration. That is also the alternative hypothesis. And again, the null hypothesis is that p is equal to 0.6. So you can see these are really the four cases that you will see, either that the claim is that the proportion is something, in this case 60%, and then the claim is HO, or that the proportion somehow differs from that, either not equal or greater than or less than. In those three cases, the claim is the alternative hypothesis. For example, a college is trying a new student registration system and would like to know if there is sufficient evidence to conclude that more than 60% of the students favor the new system. In a random sample of 520 students, 352 said that the new registration system is superior. So here we have a claim or hypothesis that we want to test, that more than 60% of the students favor the new system. So that was the case in the previous slide on the lower right-hand corner, where p is greater than 0.6. So the null hypothesis, again, is that p is equal to 0.6, and the claim is the alternative hypothesis, and this is actually what we call a right-tailed test. Next, we calculate the test statistic. This gives a position for our sample data on the normal distribution that is given by the sampling distribution for samples of size n. We have to have a hypothesized population proportion, so we use the value in the null hypothesis for p sub 0. N is the sample size, and then p hat, p with the circumflex above it, is the sample proportion, which is x over n, where x is the sample count. Again, the example where the college is trying this new registration system and wants to know if they can conclude that more than 60% of students favor the new system. Here, p sub 0 is 60% or 0.60 because the null hypothesis is assumed to be true for the purposes of calculation. The value of p hat is given by the count, 352, divided by the sample size, 520, which is approximately 0.6769. So the test statistic then is, from the formula, with sigma, the population standard deviation, put in, the values put in, approximately 3.58. Calculating the p-value. The p-value is the area beyond the test statistic in the direction of the test on the normal distribution. We can find this with tables or technology. For example, if the test statistic is 3.58 and the alternative hypothesis is h sub a p less than 0.6, that would be a left-tailed test, then the p-value would be 0.99983. If the alternate hypothesis h sub a is that p is greater than 0.6, a right-tailed test, then the p-value is 1 minus 0.99983, which is 0.00017. And finally, if h sub a is that p is not equal to 0.6, that would be a two-tailed test, and then the p-value is 2 times the smaller of the previous two, which is 0.00017 or 0.00034. The easiest way to find these calculations is with the TI-8384 calculator. If you go to Stat and then Tests, you can find one prop z-test. I believe it's option 5. For example, if our null hypothesis is that p is equal to 0.60, that's what we put in for p sub 0. If the sample count is x equal 352, that's what we put in for x, and then sample size being 520, you just put that in for n, and then you need to select the appropriate inequality for the alternate hypothesis, either not equal, that the proportion is not equal to p sub 0, or that the proportion is less than p sub 0, or that the proportion is greater than p sub 0. And then you go to calculate. The following displays at the bottom of this screen then show what you will get for the 3 different types of alternative hypotheses. For the left-tailed test, you can see the z-score, the critical value, the test statistic is 3.58, and the p-value is very large, almost 100%. If it's a right-tailed test, same z-score, same test statistic, but now the p-value is 0.00017. And here you have to be careful because the calculator will automatically put very small numbers in scientific notation with the capital E and then the power of 10. So 1.71458836 e negative 4 means times 10 to the negative 4th power, which means move the decimal place to the left 4 places and fill in with 3 zeros. On the two-tailed test, we can see that it's also a very small p-value of 0.00034. Back to the example where the college is trying the new student registration system. Since the claim is the alternative hypothesis, p is greater than 0.6, this is a right-tailed test, and so the p-value is 0.00017, very small. This is the probability of getting this sample data, or more extreme, assuming that the null hypothesis, that the proportion is actually equal to 0.6, is true. To make our decision, in general, we compare this probability to a given significance level denoted by the Greek letter alpha, the lowercase Greek a, which is usually 0.05. Usually we consider 5% to be significant. Sometimes we want to take alpha equal 0.01 to be highly statistically significant. Sometimes they'll tell you to use alpha equal 0.1, it's just 10%. So you just need to look and see what they tell you to use for the significance level for the test, and then compare the p-value to it. First of all, what we want to do is compare the p-value to alpha to see whether we should reject or fail to reject the null hypothesis. Again, the null hypothesis is our underlying assumption. So if the p-value is less than alpha, and alpha is our measure of what's considered significantly small, then the p-value is significantly small and hence unlikely. And we conclude that we must reject the underlying assumption that it must not be true. After all, it's just too unlikely. And so we reject the null hypothesis. Now, in this case, we will then support the alternative hypothesis, because remember, the null hypothesis is that the parameter is equal to some value, and the alternative hypothesis is that it differs from that value in some way. If the p-value is greater than or equal to alpha, or if the test statistic is not in the rejection region, which I'll mention in a moment, then we conclude that we can't reject the null hypothesis. It might be true. So we say we fail to reject the null hypothesis and fail to support the alternative. Here's a picture showing this rejection region in the case that alpha equals 0.05 and we have a right-tailed test. So here we have 0.05 as the area of the rejection region. The p-value is the area beyond the test statistic. So in our example, we have a rejection region with area 0.05 for alpha equal 0.05 and a p-value of 0.00017 that is way off to the right because our test statistic, 3.58, is beyond the cutoff for the rejection region, the cutoff for alpha, which on the normal distribution is 1.645. You can get that from tables or technology. That's what we call the critical value. The critical value is the cutoff for the rejection region, and the test statistic is the cutoff for the p-value. So if the test statistic is beyond the critical value, then the p-value would be less than alpha. So these go in hand. And again, the area of the rejection region is alpha, and the area beyond the test statistic is the p-value. So if the p-value is less than alpha, the test statistic will be in the rejection region. So you can use either value to make your decision, either the test statistic being in the rejection region or the p-value being less than alpha. So when the p-value is less than alpha or the test statistic is in the rejection region, we reject the null hypothesis and support the alternative hypothesis. So then what does that say about the claim? Well, if the claim or the original claim or hypothesis is that 60% of students are in favor of a new registration system, that would be the null hypothesis, and we would conclude that there is sufficient evidence to reject the claim, because in that case we reject the null hypothesis. When the p-value is less than alpha and the claim is HA, for example, more than 60%, not 60%, less than 60%, then we reject HO and support HA. So we say there is sufficient evidence, it is significant, to support the claim. That's the case we're in with our example. Since the p-value of 0.00017 is less than alpha equal 0.05, in fact, it's very small, it's very significant, we reject the null hypothesis that the proportion is 60%. And since the claim is the alternative hypothesis that the proportion is greater than 60%, we conclude that there is sufficient evidence to support the claim that more than 60% of the students favor the new system. The other case is when the p-value is not less than alpha. It's not small. Your test statistic is not in the rejection region. It wouldn't be in the tail, either the right tail or the left tail or the two tails. It's more closer to the middle of the distribution. That's when you have a larger p-value. In that case, we say that there's not sufficient evidence either to reject the claim if the claim is HO, or to support the claim if the claim is HA. So again, when the p-value is greater than or equal to alpha, there's not sufficient evidence. When the claim is HA, we say to support the claim. When the claim was HO, as in the previous slide, we say there's not sufficient evidence to reject the claim. So it's just the 4 cases. P-value small, claim HA, p-value small, claim HO, p-value large, claim HO, p-value large, claim HA. So you just have to keep straight which conclusion you're looking at for what your p-value is and what your claim is. I hope you've found this video helpful. Thanks for watching.